Hello everyone, today we will talk about vectors subspace definition and unions and intersections and sums. And in the sum part, we have two special cases of this vector subspaces sums, which are complementary and direct sum. Okay, let's talk about what is vector subspace. If we have V, U is included in V, where V is a vector space. This is a vector space, vector space, vector space. If this is also vector space, then U is a vector subspace of V. Vector subspace of V. This is what I wrote here. Okay, and this is true if three conditions hold, which are these. First condition is that the identity element of V belongs also to U, and also U is closed under addition and multiplication, and these two conditions can be shortened to into only one property, which is for all U and V belongs to U, for all alpha belongs to F, the field F, alpha multiplied by U plus V belongs also to U. So it's closed and then multiplication and addition. So let's take some examples about vector subspace and let's prove them. But before that, let's talk about why they choose these three conditions. First, since for U to be vector space, we need 8 conditions, but not exactly 3. We need first to define the class that it takes from U and gives you a vector from U. Also multiplication takes from F and multiply it by a vector from U and gives you a vector from U. So it's closed under addition and multiplication. These usually in vector subspaces, vector space generally, are automatically proven. You don't need to prove them. But in vector subspace, you need to prove them because they can go be outside the vector subspace. And also you need the 8 conditions, which are the identity elements. It already exists. And also the inverse, the additive inverse. But if for all alpha multiplied by U, this belongs to U, then minus 1 multiplied by U belongs to U. So minus U belongs to U. Therefore, it already has the inverse property. We don't need to prove it. Also, same with commutativity, associativity, multiplication identity, associativity in multiplication, and also the two laws of distributivity are automatically proven. You don't need to prove it because they are applied in the big vector space. So of course they are applied in the vector subspace automatically. Now let's talk about examples of vector subspace. Let's prove this to be a vector subspace of R. We have here R cubed, so the big vector space is R cubed. So this should this is included in R cubed. Okay. So first thing, we need to prove the identity elements. Okay. So we know that 0R cubed equals 0, 0, 0. Okay. The vector 0, 0, 0. And we need for this to belong to that, we need to for x plus z to equal 0. This is x, this is z, so 0 plus 0 must equal 0, which is true. So 0r cubed belongs to u1. Also, we need to prove these two. If we have, for example, x 0 z plus w 0 t, where these two belong to u1. Therefore, we have x plus z equals 0 and w plus t equals 0. Let's continue here. This will give us x plus w and then 0 and then z plus t. Okay, and because this is these two are true, because this and that belong to u1, therefore this implies that x plus w plus z plus t also equals 0. Therefore this plus that equals 0, so this belongs to u1. So it's closed. This is the first, this is the second, and then the third. We know it's closed under addition. We need to prove it's closed under multiplication. We have alpha multiplied by x 0 z equals alpha x and then 0 alpha z, and we know that x plus z equals 0, so alpha x plus alpha z also equals 0. Therefore this belongs to u1, so it's closed under multiplication. Okay, number 2, this is the set of continuous functions on R. We have first the identity element f equals 0. Of course this is continuous, this belongs to say R. Okay, nothing to say. Okay, because this is continuous, so it belongs to that. If f1 and f2 belongs to CR, so alpha f1 plus f2 also belongs to CR. This is from the properties of continuity. Okay, in analysis you study that function continuous function plus continuous function multiply give us continuous function. When you multiply it also with a number, a real number, it also gives us continuous function. And about u3, it's about odd functions. First we need to prove the identity elements. We have f for f equals 0, f for x equals 0, and also f minus x equals 0, and this give us also f for x give us 0. Minus 0 is just 0. So what? So f minus x equals minus f for x. Therefore this function, which is identity function, is also other function, so it belongs to u3. And also we need to prove the other thing, which is the closure. If f1 and f2 belongs to u3, by the way, we can say that f belongs to u3. Now if this belongs to u3, then then automatically f1 for minus x equals minus f1 for x. Also same thing here, they are both odd. So when you add them together, like this, minus x plus f2 minus x, and you multiply them by a number, it gives you what? It gives you alpha minus f1 x for x, and then minus f2 for x, which is the same as minus alpha f1 for x plus f2 for x. So this can be written as alpha f1 plus f2 all for minus x equals this, which can be written as alpha f1 plus f2 then all for x, but with the minus, don't forget it. This is a minus, just may write it nicely, minus parentheses. So this is a node function, so it's a closure. So this set is closed under multiplication and addition. Therefore, it's vector subspace of what? Of course, of the same this set of functions R. The field is R. The domain is R. Alright, now let's move on to the last one, which is for polynomials. First, the identity element is P, where P for x equals 0. This is the polynomial identity. Now we see that the degree of P, this gives us that the degree of P equals 0, which is less or equal 3, which is not 3, 2. So it verifies the condition of this set. Therefore, P, the identity element P, belongs to that, which is U4. Also, same thing with the second condition, which is closure. Suppose P and G belong to U4. That implies that P for x, the degree of P and degree of G are both less or equal to 2. Okay, so P for x can be written in the form where alpha k and beta k belongs to R. This can be 0. If they are 0, they give us the identity element. If they are all 0, the most important is that the degree doesn't go up 2. Okay, 2 or less than 2, and of course it can't be less than 0, otherwise it's 1 over x, which is not polynomial. Okay, and where k, we say that k is belongs to 0 1 2, 0 1 2. Okay, Now we need to add them together and multiply them by alpha and see if they give us another polynomial belongs to u4. Okay? So first we say alpha multiplied by p for x plus g for x. This gives us alpha squared, which is a polynomial of a degree 2 or less. Okay, so the degree of alpha p plus g is less or equal than 2. Therefore, alpha p plus g also belongs to u4. So u4 is closed under addition and multiplication. And then we said this as vector subspace of what? Of course, of R for X. And I said this because this is another way to write this vector subspace. When we say 2, so the degree is 2 or less. Okay. Also, this is non-example. How to prove it's not a non-example? Of course, when we see that the identity 0, 0 belongs to this, but is it closed under addition? Under addition, it's closed because positive plus positive is also positive. Okay, but in multiplication, we can multiply up by a negative number, which gives us a negative. So by counter example, we can say by counter example minus 1 multiplied by x y give us minus x minus y. And let's use a counter example. You need to use numbers like this. Okay, so this is minus 2 minus 3. We see that 2 is greater than or equal than 0. So the 2, 3 belongs to u5. But 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 minus 2 is less than 0 because it's less than 0. So minus 1, 2, 3, which is the same as minus 2 minus 3, doesn't belong to u5. So it's not a vector subspace of R squared. So vector subspace intersection. If V1 and V2 are below the vector subspace of V, then the intersection of them is also a vector subspace. Also warning, if V1 and V2 are two vector subspaces of V, then the union of them is not always a vector subspace. If you need some examples, go check the description below. There is a PDF that talks about linear algebra. You will find a lot of examples and exercises. So let's prove this theorem. First, we have, because V1 and V2 are two vector subspaces of V, then the identity element of V also belongs to V1 and 0V belongs to V2. So 0V belongs to V1 intersection V2. Also, we need to prove the closure. We have for all V1 and v2 belongs to v1 intersection v2, you have v1 and v2 belongs to v1, and here and v1 and v2 belongs to v2. So v1, because it's vector subspaces, so it's closed under addition and multiplication. So alpha multiplied by v1 plus v2 also belongs to v1, and alpha v1 plus v2 also belongs to v2. So alpha v1 plus v2 belongs to v1 intersection v2. Therefore, v1 intersection v2 is a vector subspace of v. Take this example. We have v1 and v2, two vector subspaces of R cubed. Then the intersection of them would be just this, but the conditions are both verified. From this we can simplify it a bit. We have x plus y equals 2z and x minus y equals z. You can gather them together, you get 2x equals 3z. So x equals 3z over 2. 3z over 2. We can put the 3z over 2 here, so we get, or let's do this minus this, okay? So we have 2y equals 2z minus z, which is just z. So of course y equals z over 2. So this can be written in this way: v1 intersection v2 be equal to x, y, z belongs to R cubed, such that, by the way, it's better, such that what? Let's just say that here you can say 3z over 2, and here z over 2, and here comma. So such that z belongs to R, okay? Or yeah, just write it like this, okay?